In this lesson, we're going to look at the ambiguous case of the sine law. And in the first part of this lesson, we did an investigation to see what the different cases are for the ambiguous case of the sine law. We saw that the ambiguous case occurs when the acute angle is opposite the shorter of the two sides, and we always have to have that side-side angle situation. Alright, let's take a look at the summary page. Here we can see all the different cases for the ambiguous case. So we can see when we have no triangles, when we have one triangle, and when we have two possible triangles. For the first four situations, here's when the angle A is acute, here, and the other situation down here is when angle A is obtuse. So we have two options, either no triangle or one triangle, but when angle A is acute, we've got four possible cases. And when we have these cases, it's really important that you set up your triangle if you're going to use these so that angle A is sitting in that position in order for you to compare. We also compare it to the height, right? So it's important to figure out what the height is in order to make that comparison as well. Let's start taking a look at some examples to see how we would solve these. Example 1 says solving a problem using the sine law. And it's important that they're just saying the sine law, because when you get a sine law question, the question you should always be asking yourself is this an ambiguous case? So the first step is to set up the triangle and draw the triangle that you believe they're showing you. Then you have to take into consideration, is this the only triangle? Is there a possibility that there are no triangles, or are there two triangles? Let's start by drawing triangle ABC. So it says angle A is 25 degrees, side A is 8 centimeters, side B is 11 centimeters. So I'm going to call this B and this side A. So then that would mean that this would be angle C. Now, is this an ambiguous case? Well, let's take a look at our options. Is angle A acute? Yes, angle A is acute. So we're looking at one of those first four cases. The second thing we're looking at is comparing A to B and A to H. So if we look at side A and side B, we can see that A is less than B. And the next thing we're going to look at is A smaller than H, or is A equal to H, or is A greater than H. So we're going to draw a line here to find H. So H is that perpendicular height here. Perpendicular mean 90 degrees. So we're going to use our trig, our primary trig, in order to solve for the height. Now don't get that confused with H as in our hypotenuse, because this is our hypotenuse, this is our opposite. And then we're going to be using sine because our adjacent doesn't give us any useful information here. So we'll do sine of theta as opposite over hypotenuse. Sine of 25 degrees is equal to that height we're looking for over 11. So cross multiply and divide, you get that H is equal to 11 sine of 25 degrees, and go ahead and solve that in your calculator. 11 times sine of 25, we get that that is 4.65. So H is 4.65 centimeters. Now we can write, according to A, that A is also bigger than H. So have a look at our page here. Which situation is it that A is bigger than H and A is smaller than B? That's the situation here, right? A is bigger than H and smaller than B. So that means there are two possible triangles here that we're going to have to solve for. So let's write that there are two possible triangles, right? I'm going to redraw these two triangles so we can see where they are. So the first triangle is what I've drawn there. So this is A. We're going to call this C1 and B1. This is 11. This is 8. This is 25 degrees. And we're going to solve for side C1, and we're going to solve for angle B1 and angle C1. The other triangle is the case where that arm would swing over, and this A is still here, and this C is a little bit shorter, and that arm that's still 8 centimeters long would swing over. I forgot to put centimeters here. We'd still have 25 degrees here. This is still 11 centimeters, but our angle C2 and B2 will look different than before. So we're still going to solve for side C2, angle C2, and angle B2. So we have two triangles that we have to solve completely. Let's start with the first triangle. So for the first triangle here, if I'm solving for angle B1, I would write sine of B1 over 11, because that's B, is equal to sine of 25 degrees over 8. Solving for angle B1, I'd have 11 sine of 25 degrees over 8, and that would be angle B1 is equal to the inverse sine of all of that stuff. Putting that into our calculators, you can find that angle, inverse sine, and then we'd have the brackets open here, 11 times sine of 25, all divided by 8. And we get an angle of 35.53 degrees. Now, there are lots of pieces of information that we're solving for, so I would suggest putting a box around your answer, and you can even label it in your diagram if you want. So we just solved for this 35.53 degrees, and I'm just going to put that right in there. Now, in order to solve for C1, if I have two angles already, then I'm just using the sum angle formula to find the third one. So angle C1 would be 180 degrees minus 25 degrees minus 35.53 degrees, and I would get that angle C1 is equal to 119.57 degrees. Again, put a box around your answer and put that in your diagram. The only thing left to solve for this triangle is side C1. You've got options here. I'm going to use the sine law again. I'm going to use 8 and 25 because those are angles and sides that I know they're given, and then I'm going to use the calculated 119. So setting up our ratio again, I would have side C1, wrong color here, side C1 over sine of C1, which is 119.57, and then A over sine of A, which would give me 8 over sine of 25 degrees. Solving for C1, cross multiply and divide, I'd have 8 times sine of 119.57 divided by sine of 25 degrees. Going ahead and putting that in my calculator. we get an answer of 16.46 centimeters. And that first triangle is solved. So this would be 16.46 centimeters. Now we have to do all the same math, except we've done a little bit already. In order to find angle B2, we are going to need angle B1, because if we were to do all this math again, which is essentially what you're doing, you're going to end up with the acute angle again. And we know that our calculators always give us the acute angle. So in order to find the obtuse angle, we are going to have to find its supplement. Let's start doing that. So angle B2 is going to be equal to 180 degrees minus angle B1. So angle B2 is equal to 180 degrees minus 35.53 degrees. And we get 144.47 degrees. Again, put a box around your answer and label it on your diagram. Now that we have angle A and angle B2, angle C2, we're just doing the sum angle formula again. So angle C2 is going to be 180 degrees minus 25 degrees minus 144.47 degrees. Doing that, we get an answer 10.53 degrees. Put a box around your answer and add that to the diagram. Now that we have all of our angles and almost all of our sides, all that's left is to solve for side C2. Using the sine law, we've got C2 over sine of C2, and we've got B over sine of B2. Or you could do C2 over sine of C2 and A over sine of A. And I usually do the one that was already given in the question, but either way it should give you the same answer. So here we go. C2 over sine of 10.53, and then I'd have A is 8 over sine of 25. C2 is 8 times sine of 10.53 over sine of 25. Punching all of that into our calculators, 8 sine 10.53 all divided by sine of 25 gives us an answer for C2 of 3.46. And that's in centimeters. Put a box around that and add that to your diagram. So it's quite a bit of work when you go through the two triangle situation when we're doing the ambiguous case triangle. But once you've done the first triangle, the second triangle actually goes quite a bit faster, because solving for B2 and C2, you're just using supplementary angles in order to find that out in the sum angle formula. Okay, so reminder, start the question by looking at whether or not angle A is acute, looking at the height, comparing side A to B, and comparing side A to the height, figure out how many possible triangles, and then go ahead and solve those. Let's try another example to make sure we've got this. Example 2. Martina and Carl are part of a team that is studying weather patterns. The team is about to launch a weather balloon to collect data. Martina's rope is 7.8 meters long and makes an angle of 36 degrees with the ground. Carl's rope is 5.9 meters long. Assuming that Martina and Carl form a triangle in a vertical plane with the weather balloon, what is the distance between Martina and Carl to the nearest tenth of a meter? Because I'm introducing some variables here, I'm going to say let's let h represent the height of the weather balloon, and let's let theta represent the angle for Carl's rope. but there is some ambiguity as to where this rope is going to go. So one situation I can see is if I drew the 7.8 meter rope here and put Martina here, had the balloon sitting up here for B, then I would have Carl with the shorter rope, 5.9 meters here. And then I'd be figuring out the distance they're standing this way and have the vertical height of the balloon be placed there. Let's see if this is the only situation. Okay, so we'll start by comparing our height, right, our vertical height, with our other side. But to start that, I'm missing some information here. I also need my 36 degrees. Now I can use sine in order to figure out the height. So this is my opposite, my hypotenuse, my adjacent side. Let's solve. So sine of theta is opposite over hypotenuse. Sine of 36 degrees is going to be my height over 7.8. If I do this, 7.8 sine of 36, and punch all of that into my calculator, I end up with a height of 4.6 meters. So now I have my height, and I could see, well, okay, is my side opposite M, angle M, so this is my lowercase m, compare that with lowercase c here. I'm going to get rid of the H, A, and O so we don't get confused. So I can see that that distance, Carl, is that rope length, 5.9, is less than 7.8. And I can also see, so that's my C side, and I can also see that M is greater than 4.6, which is my height. Well, this is the same situation we had for example 2. If we go back here, we've got this side is smaller than B, but bigger than H. And in that case, we can have our A value sitting here, or it could swing around and it could be sitting here. So we know that Martina is sitting here, but Carl's could be standing closer to Martina or further away with that same length of rope. So we're going to have to figure it out for both cases. Alright, so we'll write ourselves a note here. Therefore, there are two triangles. Two possible cases we can look at. So I'm going to leave this diagram the way it is, and we're going to solve for, we're going to call this one B1 and C1. And we're trying to solve this distance, right? That's what I'm trying to solve. In order to solve that distance, I need to find angle B1 and angle C1, and then I can do that. Then we're going to have to do this all over again with the other situation. Let's draw the diagram for the other scenario where Martina is still standing here, and this is still the balloon. The height hasn't changed, but now Carl is standing closer to her. And then this would be solving for B2. This is still 7.8 meters, and this is still 5.9 meters. Alright, so let's do this again. Let's solve the first triangle. So I've got sine of C1 over side C, which is 7.8, and then I would have sine of 36 degrees over side M, which is 5.9. Solving for angle C1, cross multiply and divide, and then we inverse sine it. So angle C1 would be sine minus 1 of all of this stuff. Go ahead and punch all of that into your calculator. I'm just going to round to the nearest degree, and that would give me angle C1 equal to 51 degrees. Getting angle B1, I would do 180 degrees minus 36 degrees minus 51 degrees. Doing that math, we end up with 93 degrees. And now finally solving that distance between Martina and Carl, I would do sine law again, so I would have B1 over sine of 93 degrees and 5.9 over sine of 36 degrees. Getting B1 by itself, cross multiply and divide. We solve for B1 and get that that's equal to 10.0 with our rounding to the nearest tenth because that's what they ask for, 10.0 meters. But that's just one situation. Let's see what happens if Carl is standing closer. So if we did the math again, we would end up with the same acute angle. So we know when we solve for angle C2 that we need to find its supplement. So angle C2 is going to be 180 degrees minus the answer we got for C1. So that would be 180 degrees minus 51 degrees, or angle C2 is equal to 129 degrees. So this is the obtuse possibility. Angle M is missing here. That was given as 36 degrees, same in the first part. And we need that other angle in order to solve for angle B2. Sum angle formula, so 180 degrees minus 36 degrees minus 129 degrees, we would get that angle B2 is equal to 15 degrees. Now we can figure out what that closer distance is by using the sine law again. So I'd have B2 over sine of 15 degrees and 5.9 over sine of 36 degrees. We would get that B2 is 5.9 sine of 15 all over sine of 36 degrees. Sorry, this is a 15 here. Putting that in our calculators, we get that B2 is 2.6 meters. So depending on the situation here, Carl and Martina are either standing 10.0 meters or 2.6 meters apart. We will not always get the two triangle case, but we can see from this question and our previous question that when you do get the two triangle case, it's quite a bit of work. We need to keep our work really organized. Make sure you're putting boxes around your answers and you can follow everything through. Thanks for joining me in today's lesson.